So we're starting chapter 5, and chapter 5 is a little different than the first 4 chapters that we went through. The first 4 we started with calculations, and then we looked at chemical reactions, and based on what we started with, what would we form in the end. So chapter 5 is going to seem kind of weird. It's going to seem kind of weird because all of chapter 5 is based on understanding quantum mechanics, because there's a quantum mechanical model that is what we've accepted currently, but is not necessarily the only model that could explain what we see. So the reason this is back to basics is it is the most basic that we can get to build up to explain why those chemical reactions even happen. So let's start with, what are the parts of an atom? We did this back in chapter 2, but we did not spend a lot of time on it. We kind of got right into doing calculations. So the parts that we talked about were, we had protons, we had neutrons, and then what's going to be the most important is electrons. So if you look at those 3, if you remember, the protons and neutrons are together. So those 2 are in the nucleus together. And then the electrons, we just put them outside the nucleus. We didn't say where they were, we just said they're not in the nucleus, but they're part of the atom. So if we ask which one of these are involved in chemical reactions, because ultimately the goal is to be able to look at this and figure out why some things react and other ones do. And you may know this, it's the electrons. So the more we can know about where the electrons are, not just outside the nucleus, but the actual locations of them, the more we can guess if something's going to happen or not, if something's going to be more reactive or less reactive or combined with each other or never combined with each other. So we need to know where these electrons are. But we can't tell where they are. We can tell where they probably are. So we know where there is a high probability of that electron's location. So is it closer to the nucleus? Is it farther to the nucleus, or farther from the nucleus? How many are kind of close together on the outside of the farthest away from the nucleus? So the ultimate goal of everything that I talk about, and is really going to build up to this, is to figure out where these probabilities are, because if we can tell where they probably are, we can kind of tell relative to one another which ones are going to be in closer to the nucleus and further away. So we're going to start with explaining everything in terms of something that's not an electron. So what's not an electron that we're going to start with, that later on we're going to be able to relate to the electron's behavior, is we're going to start with light. And we're going to see how light behaves. So how it behaves is the sort of odd part. So light has 2 ways that it appears to be. Light appears to kind of be like a wave, and they've done experiments to show how it's kind of like a wave. So we say it's wave-like. And then the other part, which we'll talk about in the next video, is this particle-like. And there's a reason why it's only like a particle, because when we talk about particles, they have a mass, and light doesn't have a mass. And we'll talk about it in terms of photons, which is the particle-like behavior. So I have all these different terms for light. And let's talk about those so that when I refer to this vocabulary, you'll understand and go back and relate it, that it's really the same thing as light. So light equals electromagnetic radiation. And in physics, if you think about certain electrical fields, there's like an electrical element and a magnetic element, which is why we say electromagnetic radiation. But for right now, we'll just use that term. Sometimes it's called radiant energy. So there's different ways of talking about the light. So all of light, when we talk about this radiation, the electromagnetic radiation, it leads us to the electromagnetic spectrum. So electromagnetic spectrum, if you think about spectrum, you kind of think about visible light. So there's light that we can see, and the only light we can see is visible light. It's kind of like a rainbow, right? Roy G. Biv. So you learned this a long time ago. The what you can see has a certain order to it. This goes along with the wavelike characteristics of light. So to figure out the wavelike behavior, there was an experiment that they did a long time ago, and they repeated for things other than light, and it was called the double slit experiment. So like I said before, in chemistry, you can come up with ideas calculation-wise, but we always have to do something empirically to describe what we think we know. Or someone else does an experiment, and based on their experiment, we can sort of make our own assumptions backwards from what we saw in the experiment. So this was back a long time ago. So someone named, an experimentalist named Young was the one who came up with this. So in this experiment, I'll post a video if I can find a good one, but they're all kind of a little too much. So in this experiment, that's how they saw the wave-like behavior. If it has wave-like behavior, and we're going to explain everything in terms of calculations of where the electrons are, you have to remember what you learned maybe a long time ago about waves. So if we just draw a general picture about a wave, there's certain characteristics of the wave that we talk about. So the characteristics of the wave is we have wavelength, so that's the distance from peak to peak or trough to trough. We use the symbol lambda for it. We have frequency. And the frequency is the number of these cycles. So this is one cycle. How many cycles that wave goes through per seconds. And then the last one is the amplitude of the wave. So this is actually a question on the quiz. These are the 3 terms that we have, or variables that we have to describe a wave. So it has this wave-like behavior, and the way we can see the relationship between that wave-like behavior is that we can relate them through this equation. So this kind of gets back to the electromagnetic spectrum. So looking at the terms, and we're going to write them because I don't have much space. This was wavelength. This was frequency. That's not a V. That's the Greek symbol nu. And then C, you might have seen this in a physics class. This is just a constant, which is the speed of light in a vacuum. So this lambda and the V, or nu that we see here, is what gives rise to what I was saying is the electromagnetic spectrum. So another question that's on the quiz is there's this range for this spectrum. This range is dependent on the wavelength and the frequencies. So all the way over here, and there's a good picture of this in the slides. We say the wavelength is about 10 to the negative 12 meters, so really short. And then all the way over here, we'll say the wavelength is approximately 10 to the 8 meters. So this is the length of the wave. So for that wave, this is the length of that wave. All the way down here, are things like gamma rays. And there's all these definitions in between, but we'll just do some of the bigger ones that are talked about. I'm sure you've heard of X-rays. And then we have, let's do ultraviolet light. So we'll just put UV because we're going to run out of space. And then we have the visible light, and then we have infrared, which you might have heard of, and the ones you really heard of is microwaves. And again, I'm just running out of room. And then all the way down here is radio waves. So we have this spectrum. So you have the wavelength, and then there's also frequencies associated with this. So you have this range of wavelengths. You're going to have this range of frequencies. I'm not going to put values on those because we're going to talk about how you can find the values of those. So if you look at this equation and you rearrange it, so I'm just doing the algebra. The wavelength and the frequency are inversely proportional. So if they're inversely proportional, it means if one gets big, the other one gets small. So if you have nu on the bottom of the equation, the frequency, and this gets bigger, you're going to have a smaller and smaller fraction that's here. So that's going to get smaller. So for an example, if we had longer wavelengths, you ever hear the longer wavelengths, then we're going to have, so long means like big, so if this is a big number, this is a small number, so smaller frequency values. And again, that's the Greek symbol nu, which is supposed to be, looks like a V, but it's actually a nu. So that represents the frequency. Or you could even say, which might make sense to the lower frequency. These are smaller in terms of the relationship, but normally you would say lower frequency. There's calculations for these for you to do. I don't need you to be able to do the calculation.